Let's continue our discussion of bonding by taking another example of an organic compound, okay, that is ethylene. Ethylene has a formula of C2H4. This is a possible structure of ethylene, which is the simplest alkene possible, where there is a double bond between the two carbon atoms. Okay. Now, according to the VSEPR model, that double bond, just like multiple bonds, are counted as a single effective electron pair. So therefore, around each carbon, in this case, there are three effective electron pairs. Let's recall again the electronic configuration of carbon. Carbon has an atomic number of 6. The electronic configuration is 1s2, 2s2, 2p2. And again, just like the practice that we have done before in the case of methane, let's try to distribute the valence electrons located in the outermost shell in orbitals. And if you remember, it is valence electrons that are responsible for bonding, electrons located in the highest principal quantum level. And there are 4 in this case of carbon. So this is the 2s orbital, and these are the 3 p orbitals. So these are the 3 p orbitals. This is 2px, this is 2py, and that's 2pz, and this is the 2s orbital. And of course, there is an unpaired electron in each of them. So that's 1, 2, 3, 4. And because there are 4 valence electrons in this case of carbon. Now, we have mentioned already that there are 3 effective electron pairs around carbon, in this case of ethylene. Therefore, not all of these orbitals will mix, only 3 of them. In that case, then a 1,2s orbital should mix with only 2 p orbitals to get 3 brand new orbitals, 3 hybrid orbitals, okay, which would be called Sp2 hybrid orbitals, okay. So these are the Sp2 hybrid orbitals, and the type is Sp2 because these hybrid orbitals are obtained as a result of mixing or hybridizing 1s and 2p orbitals. There is an unpaired electron in each of them. And again, if you recall this concept of hybridization, it's mixing of orbitals, and the new orbitals or the hybrid orbitals are of intermediacy in characteristics between those of s and p orbitals. And if you look carefully, the 2pz in the atom of carbon was left unmixed in this case, or unhybridized. So it should be a native p orbital, and that's the 2pz, which is native in characteristics, including, of course, shape and energy. So that's the 2pz, and we can describe it again as native, whereas these ones are hybrid. So there are, on each carbon, there are 3 Sp2 hybrid orbitals and 1 2pz native orbital. So we can now draw then a picture of bonding, in this case of ethylene. There are 3 Sp2 hybrid orbitals around each carbon. So something like that would be reasonable, okay? So 3 Sp2 hybrid orbitals around each carbon. And if you notice that the Sp2 hybrid orbital from this carbon overlaps with the other Sp2 hybrid orbital from the other carbon. This is an end-to-end overlap or head-to-head overlap, which constitutes a sigma bond between these 2 carbon atoms. If we continue with the drawing of orbitals, okay, this is the hydrogen atom, and it is the 1s orbital that's responsible for bonding, in this case from the hydrogen atom. So that's the 1s, which overlaps with the Sp2 hybrid orbital from each of these 2 carbon atoms. And again, if you look carefully, the 1s orbital from hydrogen overlaps with the Sp2 hybrid orbital from carbon. It's end-to-end overlap or head-to-head overlap, constituting again a sigma bond. So this is a sigma bond between hydrogen and carbon, and obviously that's a sigma bond between the two carbon atoms because it's formed, the sigma bond is formed by head-to-head overlap or end-to-end overlap. So that's another sigma bond which is obtained as a result of overlap between Sp2 from carbon and 1s, and that's another, this is another sigma, that's a fourth sigma bond which is formed by overlap of an Sp2 orbital and 1s from carbon. So therefore there are four sigma bonds in this case of ethylene, which are formed as a result of orbital overlap, head-to-head overlap or end-to-end overlap. So far we have not talked about the native p orbital. Now in each of these carbon atoms there is a native p orbital which can be drawn like that. Okay, so this is the 2pz of that carbon, and this is the other 2pz of the other carbon. Now these p orbitals are parallel with each other, and there is a single electron in each of them. Okay, so that's a single electron, unpaired electron. These electrons now get shared by the two carbon atoms, and this electron sharing is not only above the sigma bond, but also it's actually below. Okay, now this type of bonding as a result of electron sharing, okay, by electrons located in these unhybridized p orbitals constitutes what's called a pi bond. So there's therefore a pi bond between these two carbon atoms, in addition obviously to the sigma bond which is formed by head-to-head or end-to-end overlap. This takes us to the conclusion that in each carbon-carbon double bond there is one sigma and one pi. The geometrical shape around carbon, in this case of ethylene, is trigonal planar. The bond angle is roughly 120 because of the fact that the shape is trigonal planar. So to conclude, there are 4 sigma bonds in this case of ethylene, and there is one pi bond, and in the carbon-carbon double bond there is one sigma and one pi.